So in this lesson, I'm going to talk about intersecting planes and then also the angle between planes and the angle between a line on the plane. Let's start with the intersecting planes. So if you only have two planes that are potentially intersecting, then either they are parallel planes and therefore don't intersect, or they will intersect to form a line. Just think of any two walls that intersect with each other. The corner is a line, not just a point. Now, if there's three planes, there's lots of scenarios. I'm just sort of highlighting sort of the overarching ideas. So the three planes could all be the same plane, in which case the entire plane is the solution, is the intersection. They could intersect at one point, which is typically what happens. You think about the corner of the room, the one wall, the other wall, and the floor, for example. That's a single point of intersection. You could get no common intersection. There's various ways to do that. All three planes could be parallel, or you could have two parallel planes and then one plane that intersects those two, but still all together they don't intersect each other. Or you could have this kind of scenario where they're not parallel planes, but there's this sort of hole inside them. It's like this triangular prism that just keeps going on forever between them so that they never actually intersect all together. And then, of course, you could get the common intersection is just a line. So this will be a scenario where the three planes here, the red one, the green one, and the blue one, all intersect along this line. Or, of course, if two of the planes were exactly the same and then you took a third plane, then you'd basically be intersecting two planes again. You'd be doing a line. So those are the possibilities, generally speaking, that you might get. So we are asked to solve this system, and I want to warn you, don't use the book method. They use matrices, and it's perfectly fine, but it's not something I taught you, and I think it's just an artifact of the fact that matrices used to be on the IB curriculum many, many years ago, and it's been gone for a while, and they just haven't updated their book. So they should be using elimination, which is what I'm going to do. So first thing I'm going to do is I'm going to number these equations 1, 2, and 3, and then I'm going to try to do elimination. It doesn't really matter what variable I eliminate. Let's go and eliminate z. So I'm going to eliminate z from, let's say, 1 and 2, because it's really obvious. I can just add the two equations together. So x plus 3y minus z equals 15. That's equation 1. And 2x plus y plus z equals 7 is equation 2. When I add those equations together, I get 3x plus 4y equals 22. Let's call that equation 4. Now I got to do the same, I got to eliminate the same variable a second time, but I got to pick a different pair. So for example, let's do it from 2 and 3. So eliminate z from 2 and 3. In order to do that, I need to multiply equation 2 by 2. So I get 4x plus 2y plus 2z equals 14. That's equation 2.1. And x minus y minus 2z equals 0. That's still equation 3. And I get 5x plus y equals 14. That's equation 5. And now I'm going to try to eliminate another variable between these two. I can eliminate y without too much trouble. So let me move over to here. Eliminate y from 4 and 5. In order to do, I got to multiply equation 5 by negative 4. So I end up with 3x plus 4y equals 22. That's equation 4. And then negative 20x minus 4y equals negative 56. That's equation 5.1. And now I add these together and get negative 17x equals negative 34, and I can therefore get x equals 2. Now that I've got x equals 2, I can sub it back into, let's say, equation 5. So sub x in 5 and get 5 times 2 plus y equals 14. That's going to mean y equals 4, and then sub x and y into, and I think equation 2 is probably the easiest. So I get 2 times 2 plus 4 plus z equals 7. So that's going to be z equals negative 1. And so the point of intersection, single point of intersection, is 2, 4, negative 1. So this is basically just your regular old elimination. You could also do substitution, I suppose, solving a system of equations with 3 equations and 3 variables. That's pretty much all it is, and we ended up with a single solution, so we're happy. Now, if you get something like 5 equals 0 somewhere, you're like, well, that means no solution, so you don't even have to bother working it out any further. But if you get something like 5 equals 5, that means infinite solutions, and now we do not know where those infinite solutions are, so we're going to have to figure that out. So that's what the next example is going to look like. That's a clue, a hint. Okay, so here it is. So I'm going to, again, name these 1, 2, and 3. And I'm going to try to do elimination. Let's eliminate z from 1 and 2. So what I end up with is I can just add them together. 2x minus y plus z equals 5, and x plus y minus z equals 2. So I get 3x equals 7. Oh, look at that. That means x equals 7/3. Well, that's useful. So I'm going to plug that in. Let's plug it into, since I used equations 1 and 2, let's plug it into equation 3. So 3 times 7/3 minus 3y plus 3z equals 8. So that means 7 minus 3y plus 3z equals 8, or in other words, negative 3y plus 3z equals 1. Let's call that equation 4. And let's substitute that 7/3 into equation 2 as well. So let's see what happens there. So 7/3 plus y minus z equals 2. And so I subtract 7/3 from both sides. So y minus z equals negative 1/3. That's going to be equation 5. And now what I'm going to do is I'm going to multiply, I'm going to try to do some elimination with equation 4 and 5. So let me multiply equation 5 by 3. So I get negative 3y plus 3z equals 1. That's equation 4. And I get 3y minus 3z equals negative 1. That's equation 5.1. When I add these, I get 0 equals 0. Okay, so that means infinite solutions. Now, I already know that x equals 7/3, so this can't be a scenario, because x equals 7/3 is the only x value that'll work. This cannot be a scenario where all 3 planes are the same. In fact, you can pretty much tell that they're not the same. So instead, what we're going to do is we're going to try to find the equation of the line where they intersect. So here's what we do. We just pick one of the variables, except for in this case, the x was already fixed, so you can't do that. We just pick one of the variables and we just make it equal to a parameter. It does not matter. Remember, a line has infinite equations, depending on what direction vector you pick, how long, and what direction you're going. So, for example, let's go with z equal to lambda. So I'm going to now substitute this z equals lambda into, well, might as well plug it into one of these equations, the 4 or the 5, to get y. So I'm going to get y minus lambda equals negative 1/3, which means that y equals negative 1/3 plus lambda. So now what we figured out is that x equals 7/3, y equals negative 1/3 plus lambda, and z equals lambda. So the parametric equations of the line are going to be x equals 7/3, y equals negative 1/3 plus lambda, and z equals lambda. Now again, this equation of a line is not unique, so you may encounter somebody else doing the problem a little bit differently, and they get a different answer depending on how they chose to figure out what their parameter is. But the general principle applies. When you end up solving your 2 equations that have 2 variables and getting 0 equals 0, in other words, infinite solutions, or 5 equals 5, or whatever it might be, then what you do is you say, okay, from those most recent equations, let's pick one of those variables to just equal a parameter. And it doesn't have to equal the parameter, it's just convenient to make that happen. It could be 5 times the parameter, it could be the parameter minus 3. It doesn't really matter, because we don't know what initial point we're picking, and we don't know what direction vector we're picking, so it doesn't matter. So we pick, in this case, let z equal to lambda, and then once we have that, then we go backtrack backtrack. Once we've plugged that in, that's the parameter, we backtrack what would y equal to. And if we had to backtrack, you can backtrack even further, we would figure out what does x have to equal to. Now, of course, in this case, x was already 7/3, so it was irrelevant, but the y and the z could change. And so this is the parametric equations of the line. And if you wanted the vector equation of the line, you could also find that from here at that point. So that is the end of that one. So now let's talk about the angle between two planes, or between a line and a plane. So I want to remind you again, the angle between two lines, you use the two direction vectors v1 and v2, you do the dot product. It's going to be the product of the magnitudes times cosine theta, and theta is the angle between those two vectors, and therefore the angle between the lines. And of course, you can get the supplementary angle if you're looking for, the acute or obtuse angle, depending on the scenario. So now for the angle between two planes, so this is the diagram I'm going to refer to. I'm looking at these planes head on. So the plane is two-dimensional, but I'm looking at it from its edge, and the same thing for the other plane on its edge. So I can see the two normal vectors here and here. And the angle between the two normal vectors is going to be this angle. The angle between the two planes is going to be this angle. Of course, there's also the supplementary angle, but let's just stick to that one. If you look at this quadrilateral over here, it's got two right angles because, after all, those are two normal vectors. And so these two angles have to be supplementary because all of them have to add up to 360. If you subtract 180 from the two right angles, you get these two have to be supplementary. And therefore, this angle must be congruent to this angle. And therefore, the angle between the two normal vectors is the same as the angle between the two planes. Again, if you want the acute angle, the obtuse angle, you have those supplementary angles going on. So if there are two lines, just do the direction vectors, regular old dot product method. If it's two planes, do the normal vectors. Again, it's a regular dot product method, just with n1, n2, and et cetera, et cetera. But if you're doing it between a line and a plane, it's a little different. So here's the line, the red line here, and here is the plane, that's the blue plane. And this is the point where the red line intersects with the plane, and then this is the angle that it creates. This is the projection of that line onto the plane. This yellow line over there is the projection. So that's the smallest angle. And then I'm drawing the normal vector from somewhere along that projection. That's the normal vector to the plane. Now, since the only single vector that's easy to find from a plane is the normal vector, I'm going to try to use the normal vector and the direction vector of the line and do something with them. However, if I find the angle between the normal vector and the vector of the line, it's going to be this angle or this angle. But the angle I want between the line and the plane is not that angle, it's this one over here. However, this is a right triangle, so these two are complementary. So really, the angle alpha is just pi over 2 minus theta. So let me, if I did the dot product method over here with the normal vector and the direction vector of the line, then I would get this. But if I go with n dot v, magnitude of n, magnitude of v, and then I change that to cosine of pi over 2 minus theta, because that's, after all, what the alpha angle is. Well, remember, cosine of pi over 2 minus theta is sine theta. So n dot v equals magnitude of n, magnitude of v, times sine theta. Now, this in and of itself is not the formula for calculating dot product. However, because the vector you're taking out of the plane is the normal vector, and the vector you're taking out of the line is the direction vector, those don't mean the same thing. The normal vector is not even in the plane at all. We adjust the dot product method to calculate the angle between the plane and the line using sine theta instead of cosine theta. And it's only because they're incompatible vectors that we have to do that. And it's all because of this, the complements identity of sines and cosines. So that's what we need to do. Now, otherwise, you'd be finding the wrong angle. Be the angle between the normal vector and the direction vector is not the angle between the direction vector and the plane. That's not going to be the one you find. So by adjusting to sine theta, it fixes that error and it gets you the angle that you're looking for. All right. find the acute angle between these two planes. So again, to find the angle between two planes, we're going to do the normal vectors and do the angle between them, and that will be sufficient because it's the same thing. So n1, that would be the normal vector for the first plane, this one over here. I just read the coefficients, 1, 1, negative 1. And n2, again, I just read the coefficients 2, negative 1, 3. So I need to find the dot product, n1 dot n2. So it's going to be 1 times 2 is 2, 1 times negative 1 is negative 1, negative 1 times 3 is minus 3, so you get negative 2. Now I need to know the magnitude of n1, which is going to be square root of 3, and I need to know the magnitude of n2, which is going to be the square root of 14. Again, you can check my mental math there. Okay, so now I'm going to do n1 dot n2 is going to equal magnitude of n1, magnitude of n2 times cosine theta, because that's the dot product formula, or at least the one that relates the two different methods. So here we have negative 2 and then over square root 3 times square root 14, so that's square root of 42 equals cosine theta. Now I know I'm going to get an obtuse angle here because cosine's negative, so I'll just have to find the supplementary angle. It's no big deal. So when I do cosine inverse of, so theta equals cosine inverse of the negative 2 over root 42 with the extra decimal places is 107.9752, etc., etc. I don't really need that many. And so the acute angle is, and it's 180 minus that, so it's going to be 72.0 degrees when I put it in 3 sig figs. All right, now I want to find the angle between a plane and a line. So again, from the plane we can use the normal vector. So n vector is 1, 2, 3. And then from the line we can use the direction vector, which is this one over here, 1, negative 2, negative 1. And now remember, we still need to do the dot product and the magnitudes, but then the formula is going to change because these are incompatible types of vectors. So the dot product here is going to be 1, and then minus 4, and then minus 3, so it's going to be minus 6. And the magnitude of n vector is going to be square root 14 again, and the magnitude of the v vector is going to be square root 6. And so the formula here we're going to get is n vector dot v vector is going to be magnitude of n vector, magnitude of v vector, and then we're going to do sine theta. It's not the dot product formula, it's the formula for finding the angle between a line and a plane. So keep that in mind. This formula, I believe, is not on the formula sheet. They just have the dot product formula. You just have to remember to do it between incompatible vectors, the normal vector and the direction vector, because one's a plane, one's a line, switches to sine theta. So in this case, we have negative 6 equals square root 14 times square root 6 is square root 84, and then sine theta. So we know sine theta is going to equal negative 6 over square root 84. Okay, so this is going to give us a negative angle. Well, obviously a negative angle is not the angle they're looking for. So when we do the sine inverse of negative 6 over root 84 and we get a negative angle, we just make it positive. It's still the angle between the line and the plane. It's not the end of the world. So theta is going to equal sine inverse of, and I'm just going to make it 6 over root 84 because why not? There's no reason to have the negative there because we're just going to fix it anyway. And of course, sine of negative theta is negative sine of theta, so it's really straightforward. So here we get approximately 40.9. So that's the angle between the line and the plane. And again, we did this modified formula because those vectors we were using were incompatible. And that's the end of the lesson.